Here we have one form of the integrated rate law for a first-order reaction. And we're going to keep going with the math here, so we eventually will talk about the half-life. All right, so over here on the left, the natural log of the concentration of A at time t minus the natural log of the initial concentration of A, that's the same thing as the natural log of the concentration of A over the initial concentration of A. So that's just the log property. And this is equal to negative kt, where k is your rate constant. Next, we need to get rid of our natural log. So we're going to exponentiate both sides. So we're going to take e to both sides here, and that's going to get rid of our natural log. So now on the left side, we have our concentration over the initial concentration. On the right side, we have e to the negative kt. So we're going to multiply both sides by the initial concentration of A. So we get that our concentration of A at time t is equal to the initial concentration of A times e to the negative kt. And now it's a little bit easier to think about the graph. We can put the concentration of A on the y-axis, and we can put time on the x-axis. And this is in the form of an exponential decay. Right? So down here I've graphed an exponential decay graph just to show you what it looks like here. Right? Let's think about this point on our graph. So that's when time is equal to 0. Right? So when time is equal to 0, what is the concentration? So you would just plug in time is equal to 0 into here. Right? So you would have your concentration is equal to the initial concentration times e to the 0. And e to the 0 is of course 1. Right? So this is 1. And so our initial concentration is obviously this point right here, our time is equal to 0. This is obviously our initial concentration. So I'll write that in here. So that's this point. And as time approaches infinity, right, as time goes to infinity, your concentration of A goes to 0. Right? So as you go out here, obviously your concentration of A is going to approach 0. So that's the idea of an exponential decay graph. Next, let's think about half-life. Right, so over here is our definition for half-life. It's the time it takes for the concentration of a reactant to decrease to half of its initial concentration. Right, so if the initial concentration, right, if this is the initial concentration here, right, what would be the concentration after half of it has reacted, right? We would get our initial concentration divided by 2. So we're going to plug this in for our concentration, and then the symbol for half-life is T1/2. So T1/2. So we're going to plug this in for time. So when the time is equal to the half-life, right, your concentration is half of your initial concentration. So let's plug those in and solve for the half-life. So on the left side, we would have our initial concentration divided by 2. And then this would be equal to the initial concentration of A times e to the negative k, and then this would be the half-life, right? So we plug in T1/2 here. And so now we're just going to solve for T1/2. We're going to find the half-life for a first-order reaction. All right, let's get some more space down here. And we can immediately cancel out our initial concentration of A, right? So now we have 1/2 is equal to, this is e to the negative kt 1/2. All right, next we need to get rid of our e here, so we can take the natural log of both sides. So we can take the natural log of 1/2. This is equal to the natural log of e to the negative kt to the 1/2. And so that gets rid of our e. Right? And so now we have the natural log of 1/2 is equal to negative kt 1/2. And so we're just solving for T1/2 because T1/2 is our half-life. Right? So our half-life, T1/2, would be equal to, this would be negative natural log of 1/2 divided by k. All right, let's get out the calculator and let's find out what natural log of 1/2 is. All right, so let's get some space over here. So natural log of 0.5 is equal to negative 0.693. So we have the negative of that, so we get a positive value here for our half-life. So our half-life is equal to, let me rewrite this here. So our half-life, T1 half, is equal to 0.693 divided by K, where K is our rate constant. So here is your half-life for a first-order reaction. Now let's think about this. If K is a constant, obviously 0.693 is a constant. And so your half-life is constant. Your half-life of a first-order reaction is independent of the initial concentration of A. So you're going to get the same half-life. And let's think about that for an example. Let's go back up here to our graph, and let's think about half-life. All right, so let's say we're starting with some initial concentration. Let me go ahead and change colors here so we can think about it. I'm just going to represent our initial concentration here with 8 dots. So that's so let's say we have 8 particles. We're starting out here. So obviously this is a theoretical reaction. All right, so we're going to wait until we've lost half of our reactant. All right, so if we've lost half of our reactant, obviously we'd be left with 4. All right, we'd be left with 4 here. So where would that be on our graph? Well, at this point right here is our initial concentration. All right, this is concentration here, so we go half that. So that would be right here on our graph. So we go over here and we find this point. All right, and then we drop down to here on our x-axis. And let's just put in some times. Let's say that this is 10 seconds and 20 seconds and 30 seconds and 40 and so on. So we can see that it took, right? This took 10 seconds. It took 10 seconds for us to decrease the concentration of our reactant by half. And so the first half-life is 10 seconds. So let me write that in here. So T1 half is equal to 10 seconds. Again, a made-up reaction just to think about the idea of half-life. All right, and then let's say now we have 4. All right, so how long does it take for half of that to react? Right, so if half of that reacts, we're left with 2 particles. And on our graph, let's see, that would be right here. Right, this point would be half of this. So we go over to here. Right, and then we drop down, and how long did it take for us to decrease the concentration of our reactant by half? Once again, 10 seconds, right? So this time here would be 10 seconds. So this half-life is 10 seconds. We could do it again, right? So we lose half of our reactant again, right? And we go over to here on our graph, and we drop down to here. How long did it take to go from 2 particles to 1 particle? Once again, it took 10 seconds. Right, so the half-life is once again 10 seconds. So your half-life is independent of the initial concentration. Right, so it didn't matter if we started with 8 particles or 4 or 2. Our half-life was always 10 seconds. And so this is the idea of half-life for a first-order reaction.